Hey guys, hoping all is well with everyone. So in this video series and introduction, I wanted to create a playlist that goes through all of the 8th grade Common Core concepts and topics in response to COVID and the drastic impact that it has had on the school system. So I wanted to be able to help students in a way that is a supplemental video series on all of the topics that are covered in the 8th grade Common Core curriculum by looking at the guided practices at each individual lesson and the concepts that are covered in a step-by-step fashion that shows you how to approach these problems and how to kind of approach them from different angles, as some of these kind of topics and concepts have different ways that you can approach them. So this is going to be the first video of this series, and we're going to be looking at each module section individually. So this module is going to be 1.1 on rational and irrational numbers. So this lesson covers a couple of different things. It wants us to be able to represent fractions as their decimal equivalents, as well as the flip form of being able to write any decimal as a fraction, whether or not it is repeating or other representations of decimals. And then we want us to be able to represent those repeating decimals as well as fractions, which can be a little daunting, but there is a process that is nice and step-by-step that definitely will allow us to find those fractions. And then last but not least, we'll talk about some squares, square roots, cubes, and cubic roots. Okay, so starting with the question number 1, the directions tell us to write each fraction or mixed number as a decimal. I think when it comes to fractions and decimals, students they choose one or the other in terms of what is more comfortable for them, and it's really nice to be able to make these equivalents, not only like visually and mentally, but just to be able to be able to convert one to another, because it will allow you to solve word problems, story problems, and just in ways that it's very good at this stage in mathematics to be very versatile, to be able to adapt to any kind of question type, whether it's given to you as a fraction or a decimal. So remember, when we were talking about fractions, we just want to make sure we're understanding and comfortable with the terminology here. The number that is being divided is going to be your dividend. That's going to be the numerator. The number that's doing the dividing, or the number dividing the dividend, is going to be the denominator or the divisor. So what we want to do here for number 1 is we want to ask ourselves the question, how many times does 5 go into 2? Now, 5 can't go into 2 because it's too big of a number. So what we'll do here is we'll say that it goes in 0 times. But then what I'm also going to do is I'm going to put decimals here and here. This is going to allow me a unique opportunity to add as many indefinite zeros as I need to in order to come up with a decimal that either repeats or terminates. So the question isn't so much how many times does 5 go into 2. Now the question is how many times does 5 go into 20, which, as you can see, is going to be 4 times. So 5 times 4 is 20, and we'll get a remainder of 0. So that's the strategy that we can take for these fractions. Excuse me. So we're going to have, for our final answer for number 1, is going to be 0.4. Now, I'm going to go ahead and select here and just clear the screen here. Okay. So for number 2, we can use the same exact strategy. So again, remember, your dividend is the number that's being divided. That's going to be the numerator. And then the bottom number, the denominator, is going to be the divisor, or what's doing the dividing. So we're going to ask ourselves, how many times can 9 go into 8? And that's going to be 0 times. But again, we use this unique trick that allows us to add indefinite number of zeros. So this isn't the question of if 9 can go into 8. Now it's the question of 9 going into 80, which is going to be 8 times. And 8 times 9 is 72. We subtract the 2, borrow from the 8. 10 minus 2 is 8. and we'll bring down another 0, and we see right here that we're running into the same number here, and that's okay. It's just a very good observation to make and take note of. So 9 is going to go into 80 again 8 times, and that's going to be 72. And we're going to take that same difference, and we're going to get 10 minus 2 is 8. Now at this point, you're going to see that this is not going to change no matter how many times we multiply 9 times 8. We're always going to get 72, and we're always going to get that remainder of 8 when we subtract. So this is just going to be 0.8 repeating, okay? And it's still, again, a rational number, but we want to illustrate it as a repeating decimal. So we're going to represent it as 0.8 repeating. Okay? Let's look at the next one here once I clear the board. Okay. So the next one is going to be 3 3/4. So this one has multiple strategies that you can take, but the easiest one is going to be leave the whole number alone and add the decimal, or add the fraction to it. So what this is saying is it's going to be 3 plus 3 over 4. So what we can say here is this is going to be 3 plus 3 divided by 4. Okay. So we'll go ahead and do the long division, but we'll keep the 3 kind of on the bench for right now. So we'll do 3 plus, and again, we're going to ask ourselves the question, how many times does 4 go into 3? Okay, so we can't go in at all, but we can still add that decimal, and we can still use that trick to allow us to add as many decimals as we need. So 4 goes into 30 7 times. So that's going to give us 4 times 7 is 28. It's going to give us a remainder of 2. Borrow from the 3. 10 minus 8 is 2. And we're going to add another 0, drop down, and 4 does indeed go into 20. It goes in 5 times. So 4 times 5 is 20. We subtract, and we get 0 as a remainder. So our final answer is going to be 3, which we kind of put on the bench earlier, plus 0.75. So our final answer is going to be 3.75. Okay. Let's look at the next one here. So the next one is going to be 7/10. So I'm going to do the long division here, but then I'm going to also show you a trick for these. So again, the question is going to be, how many times can 10 go into 7? And unfortunately 10 is too big, so it can't, so it's going to be 0 times. And then I'm going to add that decimal again to give me that opportunity to add as many zeros as I need. So now the question isn't if it can go into 7, but 70. And 10 goes into 70 7 times. And that's going to give us 70 with a remainder of 0. So our answer is going to be 0.7, but another way that you can think about this is when you divide a number by 10, you're strictly moving the decimal place 1 to the left. And that's going to be for any factor of 10 equal to the number of zeros that are in it. So what I mean by that is, if you're dividing by 10, you're going to move the decimal place 1 to the left because there's 1 0. If you're going to divide it by 1,000, there's 3 zeros in 1,000, so you're going to move the decimal to the left 3 places. So that's a nice handy trick to, I'll kind of illustrate it here. So 7 divided by 1,000 is going to be 1, 2, 3. So that's going to be 0.007. Okay, so that's a nice handy trick to divide any number by factors of 10. But it only works for factors of 10 in terms of just directly moving the decimal place. So the answer here is going to be 0.7. Okay, let me go ahead and clear the board here. Alright. Okay, so this next question is going to be 2 3/8. So we can use the same strategy as before. We'll do 2 and leave it on the bench, plus 3 divided by 8. Okay, So we're going to go ahead and do the division of 8 into 3. So remember, your 8 is the divisor, 3 is your dividend. And 8 can't go into 3 because it's too big. But we can still set up this decimal here and give us that opportunity to add as many zeros as needed. 8 goes into 33 times. 8 times 3 is 24. And borrow from the 3. 10 minus 4 is 6. We'll bring down another 0 since we have a remainder. And now 8 goes into 67 times. 8 times 7 is 56. Borrow from the 6. 10 minus 6 is 4. And we'll add another 0. Bring it down. We're going to get 8 goes into 40 5 times. And that's going to be 8 times 5 is 40 with a remainder of 0. Okay, so our answer is going to be 2, which we put on the bench, plus 0.375. So our answer is going to be 2.375. Okay, this last one here is going to be 5/6. So let me go. So we have 6 going into 5. So we ask ourselves the question, 6 can't go into 5, so we're going to put it as 0. And we're going to illustrate that decimal place, giving us that ability to add zeros. So the question isn't if 6 can go into 5, now it's 6 can go into 50. It's going to be 8 times, which is going to be 48. And 50 minus 48 is going to be 2. We bring down another 0. 6 goes into 23 times, that's 18. And we're going to see here that we get that remainder of 2 again, but that's okay. So we'll go ahead and bring down the 0 here, and we'll put 6 goes into 23 times again. And we see that we get a remainder of 2 again. So what's going to happen here is this is going to repeat from 3 going forward. So our answer is going to be 0.83 repeating. Okay? And this is sometimes going to be one of those where you want to do a couple decimal places just to see if there's any change in the resultant of the remainder. But in this case, there won't be after we use 3. So it's going to be 0.83 repeating. Alright, let's go ahead and go to the next section here. Clear the board really quick. There we go. Scroll down. So now what they want you to do is kind of the opposite. They want you to take these decimals and they want you to put it in a fraction or a mixed number in the simplest form. Okay, so this is going to be, let's see here. So for number 1, we have 0.675. Now remember, as I mentioned earlier, any number is just itself over 1. That includes decimals. But what we want to do is we want to make this a rational number, which is going to be 2 integers, again, a over b, where b is not 0. And we have already satisfied that requirement because our denominator is 1. But what we want to do is we want to change this to an integer, and we're going to multiply it by some factor of 10. The question is, what factor of 10? So we have to ask ourselves, how many decimal places do we need to move in order to do that? So we need to move 1, 2, 3 to the right. So we're going to multiply by a factor of 1,000. Now I'm here, when we do this, we're using that multiplicative identity of 1. So 1,000 divided by 1,000 is 1, but I'm not changing the value of 0.675 over 1. I'm representing it in a way that is a rational number of 2 integers. So 675 times 1,000 is, or 0.675 times 1,000 is 675. And 1 times 1,000 is 1,000. Now the tricky part here is to put this in simplest form. What you're going to want to do here is determine your greatest common factor for these two numbers. What is the greatest number that both of these are divisible by. And the way that you can solve for that is by doing a factor tree. But here what we're going to do is I'm going to take an educated guess, and I'm going to say that because 25 goes into both of these numbers, I'm going to take that as a starting point. What you want to do when you're breaking these down into simple fractions, this is a pretty bulky number, or both of these are pretty bulky numbers, so that's okay. But if you want to ever do like a reduced form approach, I always recommend starting with these smaller prime numbers like 2, 3, 5, and 7. So I could have started with 5, and I would have ended up with what's going to be the same answer. So if we do 675 divided by 25, we're going to get, I believe, 27 over 40. Yeah, so we're going to get 675 divided by 25 is 27, and then 1000 divided by 25 is 40. So the question here is, can you reduce this anymore? And the answer is no. The reason for that is because there's no common factor between these two that can be divided evenly to simplify this fraction anymore. So our answer is going to be 27 over 40. Okay, so as an example, we can't divide both top and bottom by 2, even though 40 is divisible by 2, 27 is not, it isn't evenly divisible. And we can't do 3, because even though 27 is divisible by 3, 40 is not. So we'll go ahead and confirm that our final answer is 27 over 40. Let's go ahead and look at the next one here. So the next one's going to be 5.6. So this is going to be a mixed number, or it's going to be a mixed number as a final answer. But again, we can follow that same strategy. So any number is just itself over 1, and we're going to want to move this decimal to the right one place, because that'll make it an integer. So we're going to multiply both top and bottom by 10, again using that multiplicative identity of 1, and that's going to give us 56 over 10. Now what we want to do here is we want to reduce this fraction as much as possible. So what we're going to do here is we're going to say that 56 tenths, I'm going to divide by top and bottom. I'm going to start with 2 as my lowest prime number. So top and bottom divided by 2 is going to give us 28 over 5. Now what our task to do is to represent this improper fraction as a mixed number. So remember, ask yourself how many times 5 can go into 28. That's going to be 5. And then we have 3 left over, because 5 times 5 is 25. 3 over 5. So our final answer is going to be 5 3/5. And we can check that by turning 5 3/5 into an improper fraction. 5 times 5 is 25, plus 3 is 28 over 5. So our final answer is going to be 5 3/5. Okay. Alright, let's look at the next one here. So this next one is 0.44. Now be careful here, because this is not 0.4 repeating, it's just 0.44, so it does terminate. So again, this is just going to be represented as over 1, and just ask yourself the question, how many times do I need to move the decimal place? We want to move it 2 to make it an integer. So we're going to multiply by a factor of 100, because that's going to allow us to move the decimal place 2 places to the right. So that's going to be equal to 44 over 100. And again, we want to put this into simplest form. So this time I'm going to use the strategy of my smallest prime numbers and break it down kind of in pieces. So what I'm going to do is I'm going to start by dividing both top and bottom by 2, since they're both even numbers. And that's going to give me 22 over 50. Okay. And then from there, I'm going to take 22 over 50, and I'm going to divide by 2 again, because they're both still even numbers. And that's going to give me 11 over 25. And that is going to be the simplest fraction, because 11 is a prime number. Its only factors are 11 and 1. So 25 is not divisible by any of those numbers. So this is going to be our simplest fraction. So we're going to have 11 over 25. Okay. Alright, let's look at this next section here. So this section can be a little daunting, but again, if you follow the strategies, not too bad, I promise. So what we're going to do here is they want us to represent a repeating decimal as a fraction. But here we're going to introduce some algebra. What it wants us to do is we want to set this number, oops, sorry about that. We want to set 0.4 repeating equal to the variable x. Now, what we want to do first is make this number greater than 1, this 0.4 repeating decimal. We want to make it greater than 1. So we're going to multiply both sides of the equation by a factor of 10. Most importantly, remember, with equations, treat them like balance scales. In order to keep an equation balanced, we want to make sure we're applying the same operation to both sides of the equal sign. So what they have us doing here is multiplying both sides by 10. This is going to give us 10x is equal to 4.4. That's very important. Okay, so basically what happened is we multiplied the left by 10 and then the right by 10, which is going to give us that 10x is equal to 4.4. Because remember, if we multiply 0.4 by 10, we're going to move the decimal to the right, but since it's 0.444, repeating, we're going to get 4.4. Now this is where it gets a little tricky. What they want us to do is subtract x and what it equals from both sides, and this is going to allow us to make this fraction. So what I want you to think about when you see this minus x here is minus 1x. Now what is x equal to? In the very beginning we set x is equal to 0.4. Because they're directly related to each other, because they're equal to each other, because we set them equal to each other, we can represent one as a variable and one as a number, and it's still going to keep the equation balanced. That's very important. So when we do the subtraction here, we're going to do 10x minus 1x, which is going to give us 9x. And then we have 4.4 minus 0.4, which is going to give us 4. Okay? That gets rid of the decimal part of this, which is going to allow us to represent this repeating decimal as a fraction of 2 integers. Now, just remember, the same thing applies here. If we want to isolate a variable, we want to do the inverse of what's being done. So since x is being multiplied by 9, we want to divide both sides of that equation by 9. And when we do that, we get that 4 over 9 is equal to 0.4 repeating. So that's going to be our final answer, is 4/9. The reason that is going to be important is because this rational number is going to give us that repeating decimal. If we didn't subtract this 1x and this 0.4, it would be that 4.4 over 10. And we can't have that because we need to represent this in a way where the decimal is going to be repeating. Okay? Let's look at this next one. We have 0.26 repeating. So in this case, we're going to, again, set this equal to a value x. And this is going to, again, take an algebraic approach to it, but I promise you it's okay. So what we do here is we're going to multiply both sides by 100 to get a value that is more than 1. Okay, we want to make sure that this is a value that is greater than 1. So when we multiply both sides by 100, I'm going to kind of show it a little here. There we go. Sorry, it's a little messy. Alright, so now we have 100x is equal to 26.26. So remember, that 0.26 is repeating. So it repeats the 0.26. Now what it want, again, we're going to subtract that 1x. So 1x is going to be equal to, that 1x is going to be equal to that 0.26 that we defined in the very first step. So we have 100x minus 1x is going to be 99x. Okay, and then we're going to subtract that 0.26. And this is going to give us 99x is equal to 26. Now again, we want to keep this equation balanced, but we want to isolate x. So we're going to divide both sides of the equation by 99. And this is going to be the simplest form that we can have. So we're going to have 26 over 99 as our final answer. And remember, that step where we subtract that 1x on both sides, as one is a variable and one is a number, is very important, because that allows us to represent these as integers versus having a decimal involved in the final fraction. So that's a very important, crucial step. Alright, let's look at the last one here. So we have 0.325 repeating. It's the same strategy. We're going to set 0.325 repeating equal to x. So we're going to have 1000x is equal to 1000 times 0.325 repeating. So that's going to be 325.325. Oops, sorry, it's a little messy. So 325.325. And that's going to, now again, we're going to come to this step where we want to subtract 1x. And that 1x that we're subtracting is that 0.325 repeating that we had in the very beginning. Now in this case, we're subtracting off that 0.325, so we don't have to represent it as 0.325, we can just represent it as 0.325, because this is just getting rid of the decimal part of this number here. That way 325 can just be the integer that we're going to have as our numerator. So this is going to be 325. 1000x minus 1x is going to be 999x. Now we're going to do the same thing as we did with the other ones. Remember, you want to keep your equation balanced. So we have, we're going to divide top and bottom by 999. So our final answer is going to be 325 over 999. Okay. Alright, so that's going to be that section. And again, even though it's daunting, this is going to be what allows us to represent these fractions as repeating decimals. Okay. Alright, so now we're going to get into the squares and square roots and cubic roots. Yeah. So what we want to do here is we want to approximate, in this first question, the square root of 17. So one thing that's really important to keep in mind is that this number here is not a perfect square. A perfect square is defined as a number to where if you took its square root, you would get an integer. 17 is not a square root, but what we can do is approximate by taking the two perfect squares that are closest to it and kind of use that as a ballpark with the decimal that we can look at. So what I mean by that is, if I have the two closest perfect squares to 17 are going to be 16 and 25. Okay, so if we take the square roots of both of those numbers, we're going to get 4 for 16 and we're going to get 5 for 25. So square root of 17 is going to be right next door to the square root of 16. So we'll do the square root of 17, square root of 18, square root of 19, square root of 20, square root of 21, 22, 23, 24, and last but not least, 25. So the square root of 17 is going to be, if we take 16 here, this is going to be 1 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be 1 and approximately 1/8. So we have, let's see here. So we're going to have 4, so this is going to tell us that the square root of 17 is going to be plus or minus, and the reason for that is because whenever we take a square root, if you square both a positive and a negative number, it will equal a positive number. So we want to account for those two possibilities, because a negative times a negative is a positive, so that's very important to keep in mind. So when we approach this on the number line here, this is going to be approximately 4.12. It doesn't really tell us how many decimal places to approximate to, but what we can do here is if you were to break this up, this would be 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, and 8/8 would be the square root of 25. So oops, I drew an extra line here. Sorry about that. So this is the square root of 17, which is going to be 1, 2, 3, 4, 5, 6. It'd be 1/8 of the way towards 25. Okay, so it's going to be 4.12. So 1/8 is so the square root of 17 is 4.123. So approximating that will be 4.12. But again, this is kind of, they want the approximate value. So it's a strategy that you can take when you don't have a perfect square. And again, we just want kind of a rough estimate here. It's going to be an approximate value. Because if we multiplied 4.123, we would get 16.999. So going for this next one here, we're going to show that when you have a fraction of two perfect squares in the numerator and the denominator, we're going to take the square root of both of those, and that will give us our square root here. So if we take the square root of 25 over 289, that's going to be equal to the square root of 25 over the square root of 289. That's going to be equal to 5. The square root of 289 is going to be 17. Okay. Now the cube here is saying that x cubed is equal to 216. That means that some value x, when multiplied by itself 3 times, is going to be equal to 216. So the number that we would multiply by itself 3 times is going to be 6 times 6 times 6. And the question that a lot of times comes up is it possible for, like we saw here, as a plus or minus situation? The answer is going to be no for this. If it's going to be a positive result, there's no negative number you can multiply or you can cube to equal 216. The reason for that is if you took -6 and cubed it, that'd be -6 times -6 times -6. And that's going to give you -6 times -6 is positive 36. But if you multiply it by -6 again, your answer is going to be negative 216. So there's no possible negative number you can cube to reach a positive result. So that's why we don't have the plus or minus here, because all of the values that are going to be cubed to equal a positive perfect cube have to be positive. Okay, and now for this one, we're gonna, so this is gonna be 6. Okay, oh, I see what happened. This is gonna be the cube root of 216, which is gonna be equal to 6. Sorry, the page cut off a little bit, but this is gonna be 6. Alright, so kind of using the strategy, these are all gonna be approximations. So again, we wanna have kind of a strategy going into these, and since we can't use a calculator, what we want to do is we want to make like a number line and then use the number line as like fractions of between the two perfect squares. So the two perfect squares that the square root of 5 falls between in is the square root of 4 and the square root of 9. Okay, now they only want one decimal place, so the square root of 5 is going to be right here. Okay, and we have square root of 6, square root of 7, square root of 8, square root of 9. So what we're going to do here is this is going to be 2, this is going to be 3. So the square root of 5 is going to be 2 point, and then 1, 2, 3, 4, 5. So it's going to be 5, and it's going to be 1/5 of the way to the next perfect square. So the square root of 5 is going to be 2.2 to one decimal place, because 1 divided by 5 on this number line would be 0.2. Okay. For the square root of 3, we're going to do the square root of 1 on the left for that perfect square, and then we're going to set square root of 3 here, and the square root of 4 is going to be the next perfect square. So go ahead and define your your square roots. This is going to be 1. Square root of 1 is 1. Square root of 4 is 2. But it's going to be closer to the square root of 4. So let's see here. If we did the square root of 2, square root of 3, and the square root of 4, this is going to be closer to 4. So this is like 1, 2, 3, 4. So the square root of 3 is about 3/4 of the way. So we're going to say 1.7, since 3/4 is equal to 0.75. Okay, and again, these are all approximations, but these are getting into irrational numbers. One thing I want to highlight about that is irrational numbers cannot be expressed as a ratio of two integers. So they don't terminate. They go on forever, but they're not in a way that repeats decimals in any kind of pattern. Okay, so the last one is going to be the square root of 10. So what we're going to do is we're going to take the two perfect squares that are closest to it. It's going to be the square root of 9 and the square root of 16, but we see that the square root of 10 is much closer. So we say that this is the square root of 10, square root of 11, 12, 13, 14, 15, 16. So this is going to be 1, 2, 3, 4, 5, 6, 7. So we have 9, or we're going to have the square root of 9, which is 3. And then we have 1/7, or let's see here. Oops. It's going to be 3 and 1/6 practically. So we have 1, 2, 3, 4, 5, 6. So it's 3 and 1/6 toward the next perfect square. So this is going to be 3.1, but we're going to round that up, or to one decimal place. It doesn't ask us to round. So it's just going to be 3.1. Okay, so again, these are approximations, but we can definitely use this number line strategy to kind of see the decimal place of the square root. That again, these are going to be irrational numbers, so we're kind of approximating here because they're not going to be perfect squares. They're not going to result in an integer as a solution. This last question is just kind of an essential question, check-in. What is the difference between rational and irrational numbers? So just as kind of a definition recap, rational numbers are numbers, they're numbers in which they can be expressed as a ratio of two integers, a over b, where b is not 0. And the reason that that's important is because at this stage in mathematics, we know that we cannot divide by 0. It's like almost against like mathematical law, so to speak. So we don't want to do that, and we want to make sure that when we make a terminology definition, that we still account for that attribute or rule that we need to keep in mind. They can be integers. They can be fractions as a ratio of two integers, or they can be repeating decimals. Okay, so those are going to be rational numbers. Irrational numbers do not repeat or terminate. They go pretty much on forever. And a lot of the times you're going to notice that the irrational numbers are going to be square roots of non-perfect squares a lot of the time. So as we saw here, these are all irrational numbers. Square root of 5, square root of 3, square root of 10. One thing you might notice right off the bat is square root of 5 and square root of 3 are prime numbers. So a lot of times irrational numbers are square roots of prime numbers other than 1. I'm trying to think if 1 is a prime number. 1 is not a prime number, sorry. There's a specific rule with it, but 5 and 3 are prime numbers, so we can see that those are irrational. But they do not repeat or terminate. Very important irrational numbers to become familiar with are pi and exponential e are both irrational numbers. They are constants, but again, they go on forever. So those are two important irrational numbers you want to kind of get familiar with. You don't really have to know too many of their decimal places, but it is good to kind of get familiar with their origin, where they, their approximations, just to kind of help you understand the idea of irrational numbers. But this does complete the guided practice for section 1.1 on rational and irrational numbers. I hope this helps you guys out. I hope this definitely represents a step-by-step fashion to solving some of these problems. If you guys have any questions at all, please don't hesitate to message me or reach out. I'd be more than happy to answer questions you have. But I will be continuing on with the modules here, and if you have any questions or any requests for any certain sections, I can definitely get them up sooner than later in what would be chronological order. But thank you guys so much for watching, and please take good care of yourselves, and hope to see you soon. Bye.